Dear students, in this class, let us discuss about growth of charge in a LCR circuit. So we have learned the growth of charge in a capacitor using a CR circuit and also the decay. So I will just summarize what we have studied so far. So CR circuit, growth and decay, and LR circuit again growth of current and decay of current. Okay, and then what bits you have to remember in case of CR? You have to first you should know how to apply the Kirchhoff's voltage law, and then it's just the derivation. You can do it. Then you get the final equation. You should remember the equation for the growth of charge, and you should also remember the graph, and you should also remember the time constant tau is equal to RC. It's good to remember the power dissipated in case of a capacitor. Similarly, in case of inductor, you need to know the Kirchhoff's voltage law, how to apply, and then the final equation for the growth of current and the power dissipated, the time constant. That's all. And decay, it's just the growth without the battery, so it will be easier to solve a decay curve. So just remember the decay curves and growth curves clearly. That will help you a lot. Okay, now we will move on to LCR circuit, which is containing three components: a inductor, capacitor and resistor. And as shown here, initially we connect the circuit to a battery E, and then you have the circuit complete and current starts increasing in the circuit. So you have L. What is L? You can write. What is C? You can write. What is R? It's a resistor. E is the battery in the circuit, and all in series. So when G1 is closed, what happens when G1, gap 1 is closed? The charge starts getting stored across the capacitor. So here, because this side is plus, so capacitor, here you have plus charges and here you have minus. Okay, so actually electrons move in this direction, opposite to the direction of the current. Current is in this direction. So for now we can just ignore this gap. We'll not worry about it now. Let us say that that gap is not there. So you have current flowing in this direction. Okay, so C starts charging, I increases, and as a result field around L also increases. So you remember that in CREA CS. Okay, you remember that energy is stored in case of a inductor as a magnetic field, whereas in case of capacitor it is stored as charge. Okay, next what happens? Let us say initially we take the charge to be 0 and current to be 0. So initial conditions are at t is equal to 0, charge on C is equal to 0, current is also equal to 0. At t is equal to t, or we can just say t greater than 0, what it is that we are going to calculate. So that is our task. Okay, we have to derive. So look at the circuit. From the previous derivations, the voltage across the new page after, insert new page after, sorry, I should have done it earlier, after. Okay, that should be enough. So we are going to apply the Kirchhoff's voltage law first. So when you apply Kirchhoff's voltage law, so applying Kirchhoff's voltage law, or Kirchhoff's, some people say Kirchhoff's loop rule, something like that. So applying Kirchhoff's voltage law, potential difference across the capacitor is Q by C plus Ri across resistor across C across R is equal to minus L di by dt plus E. So this is battery EMF, and this is what? Self-induced EMF. You remember I mentioned that these two are opposite to each other. As before, we just do the rearranging. Q by C plus Ri plus L into di by dt is equal to E. We know that I is equal to dq by dt, and substituting that we get Q by C plus R into dq by dt plus L into d square I by dt square is equal to E, or is equal to 0. Okay, I call this equation 1. So this is a differential equation, second order differential equation. So this explains the variation of, sorry, it was a mistake, variation of Q in the circuit. But this is a differential equation, we cannot plot it as it is, so we have to find the solution. Okay, so we do a little bit of rearrangement. So we just keep the d square q by, as you do in mathematics, we make the second order term free of any coefficients, plus r by L into dq by dt plus q minus ce divided by LC is equal to 0. Okay, it's a bit too many variables, so what I do is I call let x is equal to q minus ce and 2b is equal to r by L, we substitute for some constant, and k square is equal to 1 by LC. I will tell you later why we use these substitutions, not something else. So therefore d x by dt is equal to dq by dt, and d square is again d square. So okay, now if you make these substitutions, what we obtain is d square x by dt square plus 2b dx by dt plus k square x is equal to 0. So that is the equation you obtain after substituting for after substituting for q and r by l and 1 by lc. This is the differential equation of second order. It is a standard form, you might know better than me. So it has a, so it is in the standard form, and it has got a solution of the form x is equal to e to the power alpha t. Okay, we will find out the particular solution. So therefore dx by dt is equal to alpha e to the power alpha t, and d square x by dt square is equal to alpha square e to the power alpha t. Substituting in equation 3, we substitute this in equation 3. What do we get? Substituting in equation 3, you get alpha square e to the power alpha t plus 2b alpha e to the power alpha t plus k square e to the power alpha t is equal to 0, or alpha square plus 2b alpha plus k square is equal to 0. So just divide it by alpha t on both sides, you get that. We treat this as a quadratic equation in alpha, okay, and find the roots, find out the roots. You know that if it is a quadratic equation, then the roots are alpha is equal to minus b plus or minus square root of b square minus k square. So you know that roots of the equation x is equal to minus b plus or minus square root of b square minus 4ac divided by 2a, if I am not wrong. So you have to use this here, and then you get that equation of this form. So we are not going to do the steps. So this has two solutions. This has two solutions. One is alpha is equal to minus b plus square root of b square minus k square, and which we can call as alpha 1, and alpha 2 is equal to minus b minus square root of b square minus k square. Therefore, we have x is equal to e to the power alpha 1 t and x is equal to e to the power alpha 2 t are the two solutions. Then you know that the general solution will be, therefore the general solution will be a linear combination of the two. So we can write x is equal to a1 e to the power minus b plus square root of b square minus k square plus a2 into e to the power minus b minus square root of b square minus k square. So I call that as equation 4. Okay. So since x is equal to q minus ce, and that is implies we can call that as q minus q naught. Q naught is the charge stored on the plates of the capacitor when it is fully charged. Okay, so this is when it is fully charged, and that is equal to a1 e to the power alpha 1 t plus a2 e to the power alpha 2 t, or q is equal, so that is the thing, or that implies q is equal to q naught plus a1 e to the power alpha 1 t plus a2 e to the power alpha 2 t. So that is the equation that describes the growth of charge in the LCR circuit. Now we have to find out, there are two unknowns, these two. Alpha we know, we have substituted for alpha, but we don't know a1 and a2. So to find a1 and a2, you know how to do it. Put the initial conditions. So at t is equal to 0, q is equal to 0, and that implies a 0, sorry, that implies 0 is equal to q naught plus a1 plus a2, that implies minus q naught is equal to a1 plus a2. Now let us differentiate to find another. We need two equations to find out two unknowns. So differentiate 5 with respect to t. So what we get, I is equal to dq by dt is equal to I is equal to a1 alpha 1 e to the power alpha 1 t plus a2 alpha 2 e to the power alpha 2 t. So again put the same condition, at t is equal to 0, q is equal to 0, or I is equal to 0. So if you put that, a1 alpha 1 plus a2 alpha 2 is equal to 0 is the condition. Or you just substitute for alpha 1 a1 into minus b plus square root of b square minus k square plus a2 into minus b minus square root of b square minus k square is equal to 0, or you just do the rearranging of the terms. So you take the b's common and square root of b square minus k square as common. So if you take b as common, you get a1 plus a2 plus square root of b square minus k square as common term. Then you get a1 minus a2 as a common term from those two, and that is equal to 0. And you know that a1 plus a2 is equal to minus q naught. So that implies a1 minus a2 is equal to b q naught by square root of b square minus k square. That implies a1 plus a2, and we know a1 plus a2 is equal to minus q naught. Okay, from this step again we have to move further, couple of more steps to follow. You can look at it in the book So we have got, so you add those two, adding, subtracting, adding, you get, if you add you get A1, by subtracting you get A2. You should also do some work, okay, so that's why I'm not doing those steps. So you get A1 and A2. So substituting A1 and A2 in equation 5, in the equation 5. Where is the equation 5? We will see. Now this is the equation 5, so you have to substitute for A1 and A2 in that equation. So what we get substituting that is Q is equal to Q naught minus half Q naught into 1 plus B by square root of B square minus K square into e to the power minus B plus square root of B square minus K square plus half Q naught into 1 minus B by square root of B square minus K square into the last term e to the power minus B square minus K square root of. So that is the equation, or rearranging this a little bit, because that e to the power B is common. So of course, sorry, there is time here in the exponential. So we can write Q is equal to Q naught minus, common term is again Q naught by 2, Q naught by 2 into e to the power minus Bt in the bracket 1 plus B by square root of B square minus K square into e to the power B square root of B square minus K square into T. Okay, second term plus 1 minus B by square root of B square minus K square into e to the power minus B square minus K square into T. So this is the expression for the growth of current, growth of charge in the LCR circuit. To know the current, growth of current, what you have to do, you have to just differentiate it. I know you don't want to do that, but in case if somebody asks you how do you get growth of current, then you have to just differentiate this with respect to time, and then you get it. Okay, there are a few cases to be discussed. Case 1 is, what if B square is greater than K square? What if B square is greater than K square? If B square is greater than K square, square root of B square minus K square is real. Square root of a positive integer is real. Therefore, that implies charge grows exponentially. Okay, so grows exponentially. So it's just an exponential growth. For charge versus time. Okay, grows exponentially. And it reaches a maximum value. Okay, this is also known as dead beat, or also said overdamped. Second case, if B square is equal to K square, A steep rise, steep growth, steep or quick growth. So you can we can plot that as a bit steeper, bit steeper, maybe it's a bit more steeper, that's all. So this is known as critically damped. Q T. Charge rises exponentially but fast. That's all. It is an exponential curve. You put v square is equal to k square. What happens then is this exponential term in the bracket will be 0. All those terms vanish. So you are left with only q naught minus q naught by 2 e to the power minus bt. Okay. Next case is a bit lengthy one because we get into some problem there. If b square is less than k square, square root of b square minus k square is not real, or it is imaginary. Imaginary means, so for that what we do is we write it as minus square root of b square minus k square is equal, we can write it as square root of minus into k square minus b square. Here k square minus b square is greater than 0. Okay, so that is real, square root of that. So and that we write it as j omega, where j is equal to square root of minus 1. So it's actually written as square root of minus 1 into square root of k square minus b square. And this is j, and that is omega. Maybe I can use a different pen to avoid confusion. Okay, so that is j and that is omega. So j is equal to square root of minus 1 and omega is equal to square root of k square minus b square, which is a positive integer, real integer, need not be positive. So therefore we have this, and then we just do the substitution in the equations. As I mentioned you here, this equation, the one we got, we call that as equation 6. Here, equation 6. So we substitute in equation 6, and what you get is q is equal to q naught minus q naught by 2 into e to the power beta t into bracket 1 plus b by jw e to the power I omega t j omega t plus 1 minus b by jw into e to the power minus j omega t. that is q naught minus q naught by 2 into e to the power minus bt. So we just write down e to the power j omega t plus e to the power minus j omega t plus b by j omega into e to the power j omega t minus e to the power j omega t. We just do some rearranging the terms. I will bring 2 outside. So q naught minus q naught e to the power minus bt into e to the power j omega t plus e to the power minus j omega t by 2 plus b by omega into e to the power j omega t minus e to the minus j omega t by 2j. They all are our familiar cos and sine functions. So that is q naught minus q naught e to the power minus bt into, this is nothing but the cos omega t, and that is sine omega t. So this is cos omega t plus b by w sine omega t. Sorry, just a minute. W stays with cos. Or in other words, you can write, you can see it in the book, take the q naught common and write 1 minus e to the power bt minus e to the power bt into omega cos omega t plus b sine omega t divided by omega. Okay, so and that is equal to q naught into one minus e to the power minus bt by omega into omega cos omega t plus b sine omega t. Let omega is equal to r sine theta and b is equal to r cos theta. R and theta are constants because omega and b are also constants. If you take that, then that implies q is equal to q naught into 1 minus r e to the power bt minus bt by omega theta cos omega t cos theta sine omega t, and we use the trigonometric identities q naught into 1 minus r e to the power minus bt by omega into sine omega t plus theta. So that is the equation we obtain. So what this represents is a damped oscillatory. So it is like sorry, like that, and then something like that it represents. It has two parts, we will discuss that, quick rise and then oscillatory. So this is known as damped oscillatory. So this is, and the time period of oscillation is nothing but t is equal to 1 by f, that is 2 pi by omega, and that is nothing but omega we have already taken there by square root of k square minus b square. So that is the reason why we took omega as square root of k square minus b square. It is a frequency term, angular frequency term. Okay, that is why it was taken that way. And b is also a kind of term equivalent to k. Okay, so again we substitute, for k and b, and what you get is t is equal to 2 pi by square root of 1 by LC minus R square by 4L square, or F is equal to 1 by 2 pi square root of 1 by LC minus R square by 4L square, and that is the frequency of oscillation. Now if we plot all the three graphs here, one is, as I told you, first case under damped and over damped, and then this is damped oscillatory. Of course, they all just let me erase this. So it is slow raise, but it will converge to that. So they all converge to the same value. So this is case 1, this is case 2, and this is case 3. Okay, case 1 where it was b square minus k square was positive, or real, it had a real value, and then here b square is equal to k square, or square root of the term inside the square root was 0, and in this case the term inside the square root was negative in case of damped oscillatory. So this is damped. This is, I have told you already, critically damped. This is over damped. Okay, so with that we complete the growth of charge in a LCR circuit. So this is could be a long answer type question, but you will be asked to discuss either you derive the equation and discuss first two cases, or you just start with the equation and discuss the cases. Question will be like that. You will not be asked to derive the entire derivation, because your questions will be for 7 marks. So anyway, it is good to know this clearly. And then there is a decay of charge in LCR circuit, that is also a bit lengthy derivation like this, and those two are the two lengthy derivations in this unit. No need to worry. If you have any doubts, just ask me, sir, on this page, this step, what is it? Why should it be like this? Okay, and all